Welcome to our presentation done by myself and three people at the Advanced Photon Source and my colleague Baronova in Russia. You see here on the first page already what we want to bring forth, namely on the left side is a reflection, X-ray reflection at 8 kV from a flat thin crystal as might be bent in an X-ray microscope. Usually these are spherically bent, and you see the reflection is very ratty. In the middle and the right side you see the reflection from, as it should be, namely completely uniform across the surface, from quartz as is the left side as well, and from silicon. So the X-ray reflection can be completely uniform across the surface, and of course that's what we count on with reflection from thin bent wafers. So we want to work toward making those better. Usually, or almost always, the microscopes are tested with X-rays and some kind of a mesh or something to see that they really work, and usually they work well enough. But here we are trying to do state-of-the-art measurements, microrad, microradian angular resolution and submillimeter spatial resolution, rather than integrated measurements as you might want to do if you were to measure a focal point or something like that. We want to use quartz as our example, in particular the 1 0 minus 1 1 reflection, or its sister, namely 0 1 minus 1 1. And it's important to keep the order of the Bravais Miller indices in mind. They are different. They reflect differently. Here's what made us start on this. You see on the top line the visible light image made by a particular X-ray microscope from the reflection of the crystals of the quartz surface, and at the bottom row the same X-ray microscopes was now used for X-rays. This was done by Christian Stuckel at Rochester. And on the right side you have the X-ray image with a fair amount of non-ideal what seems to be scatter around the focal point. Remember, this is actually very small. It's hard to read, but you can go to his original article to get all the details. We use the topography at 1BM at the APS, which is made for a very careful local examination of the reflection from crystals. We have X-rays coming in from the left. They go to a conditioning crystal which makes them very uniform and unidirectional. It makes them unidirectional and very monoenergetic, and spreads them out over the sample. We use 8 kV, whereas the microscope is using 1.8 kV or thereabouts, so that the X-rays will reflect from roughly the same volume that the crystal might have. Now these are thin crystals, at least the ones we are most interested in, like this, and they are made flat by a flat substrate. So there are all kinds of things where it can go wrong, namely on the surface of the substrate, the surface of the crystal itself, some strain in the crystal, some induced strain, all kinds of terrible things could possibly happen. And we can see that very accurately by changing the angle here under which the crystal sees the X-rays, and that makes the reflection change as a very sensitive function of the angle psi here. Typically psi is done in steps of 2 microradians over a range of like 2 milliradian, not very small range. This is what it is in practice. You see here the X-rays coming in from the top from this crystal here. The X-rays go along this path and bounce off like this, and our camera is over here. I want to emphasize, want to remind you something that you all know, and if not you should have known, as we should have known as well, that the reflection of this particular kind of quartz differs from this particular kind of quartz. And you see here the working curves as computed by a very handy website by the X-ray server, Stepanov. No. Well, anyway, it's the X-ray server. You can find it. And you see the full width F max of one of them is 50% or so less than of the other one. Of course, the integrated reflectivity, the area under this curve, is the same factor, roughly smaller. And you have to specify in your microscope which version of quartz you want. If you want to try for the best resolution, angular resolution, you should really take the black curve, which is 0, 1, minus 1, 1. Sorry, which is 1, 0, minus 1, 1. And not the red curve. But if you don't have enough photons, you should by all means use the red curve. And you have to watch out. In our case, we had troubles ourselves in specifying these particular cuts. When you measure the rocking curve, as you normally do with a photodiode, for instance, you measure average over an area, and that's substantially wider for these flat, thin samples than it could be. So this is what's ideal. We almost get to the ideal in our setup. This is for silicon, but we also did it for quartz. It's the same thing. And this here is for 2 quartzes. One what should be ideal, and one that we measure on the picture I showed you before. It's this kind of picture over a typical area, maybe like this. This is the intensity at peak reflection. It's very uniform in this case. You see some spots that are maybe places where the CCD may mess up a little bit or something. But basically, this is really terrible reflection. The full width F max, which is a measure of the strain in the crystal, can be found locally from our measurements. And in a thick crystal like here on the silicon crystal, the full width F max is perfectly uniform. And if you measure the rocking curve over a large area like this area here, you get almost a theoretical value. If you do it for here, you get some kind of average value that is very much wider. Of course, this is not what you want for an X-ray microscope. I have to say that we assume that the same qualitative character of the reflection for a flat crystal will carry over once the crystal is bent. There's additional widening and there could be additional troubles, of course, but the thought is that the bending is not so severe that it will change the reflection substantially. This is a sample where we try to compare the exact same quartz, thin, optically attached to a quartz substrate, which gave you this reflection, the substrate itself, which gives you this reflection, and another thin sample that actually fell off. We intended to have 2 of them, so that we had more than one sample. And it shows interesting things, namely damage to the original crystal, to the substrate, and also some inkling of where the edge used to be. So apparently the optical attachment may do some damage to the substrate, which implies that it might do some damage to the thin crystal itself, which suggests to me at least that maybe in the optical attachment there could be some hidden troubles that causes the reflection to be not quite as ideal as we want it to be. Oops, wrong direction. One thought was that polishing might make a difference. It turns out that's not so. Here are 3 surfaces of thick quartz crystals, all the same kind, polished in 3 different ways. This is obviously the best, the most uniform across the surface. And these ones are quite okay. They are all within 2 microradians. The full width max is within 2 microradians, so they should not give you all the scatter that we see in the microscope images. Now the absolute value is not what it should be, but that's, we suspect, due to a problem in our setup that we have to fix next time we do this measurement. Now our next step would be, of course, to do something similar for a bent crystal, but that is substantially more cumbersome, because for a bent crystal in our setup produces a very thin line, X-ray reflection that is too thin to be seen by the CCD. The CCD itself has can see only like 40 microns or something, but this X-ray reflection, which is suggested here by the red line, is less than a micron in thickness. So we have to do something that people do routinely, which is to move an absorber through that line and then see when the X-rays that come through disappear, and they will then the resolution, the spatial resolution, is given by the motion of this slit or this edge through the system. So we will on the CCD see something as broad as this, whereas the actual X-rays are like this. And we hope to do that in the near future. Now our conclusion is partially sort of obvious, namely when you want to make good X-ray crystals, you should start with a good bowl and then polish well. So this is what we can do. And of course we have to identify and then fix the issues with the attachment. So our measurements show that we should be able to do very much better than what we are doing. But whether that is important for your application, we cannot say. Maybe the microradian deviations that we worry about are completely irrelevant in what you have for your particular setup. If there are any questions, please let me know.